for, or are they actually like really physically some shape that has these properties that you want? Or
I want to say,
are they more like just a label for this? You know what I mean?
So the, in certain materials, though, in topological insulators as a class, the wave functions of the electrons are knotted in such a way that each of them has a characteristic, like topological variant. And the way that variant is extracted is how it is knotted, how the wave function is knotted, and it's very particular to each material. Can't comment more on that because I'm just by no means an expert.
Tell us about this.
On the far right? No, in the middle?
The second one.
This is a representation of what is thought to happen in the how do you say when two things come together? The interface. The interface of the surface state of the topological insulator, so the conducting state and the insulating state. Basically, there's, you know how you say that the coffee cup and the donut are pairs. They have these pairs that are related by their topological invariance. You could say that these two are a pair like that, but there's no smooth transition from one to the other. There is, in the middle, something that cuts them, that makes this happen.
They are not homotopically equivalent.
Sure.
What about the last one? What about the last
So
one?
the last one is just, it's basically the simplest form of a three-dimensional knotting of states, of wave functions.
Is this right to say that this whole topological insulator thing is because at the surface, the conduction bands are connected, but inside they're not? So there's a change in topology of conduction bands?
I would say so.
Okay.
I mean, it probably has some. People are still trying to, I want to draw attention to the fact that this was experimentally confirmed in 2008. It's 2011. They're still trying to figure out what's going on, right? It's a very hot topic. Hundreds of papers have been published like a month on topological insulators, and it's something that's very fun because the people that I was working with, they're experimentalists, but they kept going back and forth between the theorists. At MIT, you have a condensed matter theory group, and they went back to them, like talked and like argued, and then came back to the lab and did experiments and stuff like that. So they're still trying to figure out what the hell's going on. That's exciting. So this is how graphene and bismuth selenide are related. And so before I got there, I was working under Nathan Gabor. He's a postdoc at MIT. And what Nathan did with his group, he was like the token optics guy. Like they did graphene experiments that had no light involved. So basically they applied currents and voltages to flakes of graphene and see what was going on. And what Nathan did was couple these kinds of experiments with light. So he optically excited flakes of graphene and saw what was the kind of mechanisms that governed in graphene and for photocurrent generation. And so what he found out is that actually when you photo excite a flake of graphene, the resulting current is due to a photothermoelectric effect. We here know what the photothermoelectric is. Basically, people before this paper was published thought that when you optically excited graphene, the resulting current was due to a photovoltaic effect. That there was an inherent electric field within the flake, the one atom thick flake that generated this current, right? But this paper dispelled those rumors, I guess you could say. And so what we wanted to know is whether these same mechanisms were at work in bismuth selenide. And the reason why is because bismuth selenide is very much like a graphene lookalike at its surface. So we wanted to apply the same kind of measurements from graphene to bismuth selenide and see if this was what was happening in bismuth selenide. So that's how we did that. And so I'm going to talk a little bit about the photothermoelectric effect. It's pretty much what it sounds like. Basically light and heat generating a current. Basically, you have this relationship that says that if you have a thermal gradient, a temperature gradient, you create a potential difference. And that's related by this, which is called the Seebeck coefficient, which is related by other stuff. But it's exactly what it sounds. It's just light and heat interacting to create current. And so what I also want to point out is that it's really interesting is that I say that bismuth selenide is a good, it's a topological insulator, and that it was confirmed only in 2008. Yeah, well, bismuth selenide has been around for like decades. I found papers on bismuth selenide from like the 50s. But people hadn't looked at bismuth selenide through the lens of topological insulating things that matter until 2008. Bismuth selenide is used like, it's probably, you can probably find it in fridges. Like, it's not a new material. It's just that people are looking at it very recently with new eyes. And so that's why it was also cool that you found this, you know, it's relevant in this case because you're looking at also thermal effects in the lives. I put this picture up because it just looks really cool and whatever. This is the toys that the experiment was working with.
So it's a real thing.
It's a real thing. Yeah, this is actually a fabrication facility at MIT. And basically what it is just a big friggin' chamber in which you just have a substrate, which is just what you're going to deposit your flakes on, and you shoot ions at it. And you construct your flake. You grow your flake. And so I just thought it looked cool. Unfortunately, I didn't take part in any of this. I didn't fabricate any of the devices that I worked with. I just kind of got the hand-me-downs. And so this what is called, the technique is called molecular beam epitaxy. Yeah.
So for your plant, would you use the business selenide or?
It's like, we use samples that were like a year old. So I got hand-me-downs, unfortunately.
Well, unfortunately.
Because, as you will see, it led to some problems.
Oh.
So this is just a general schematic of the fabrication process of the bismuth selenide. This brown flake is actually the bismuth selenide. You had it on a insulating substrate, and then you had other stuff too. I'm not going to go into it, it's just kind of boring, but it's basically a dielectric that makes sure that it's insulated and that everything's in good condition. And yeah. I wanted to show you guys what the actual flakes that I worked with look like. And these were fabricated using the facilities that I showed you before. And so this is kind of like scale. This is 8 microns big. And the bismuth selenide, this is actually a top gate that's made out of gold. And the bismuth selenide is underneath. It's like this flake, a horizontal direction. And these are just contacts. They're just contacts. Basically, like I said, I got hand-me-downs. These were devices that were fabricated for entirely different purposes. They were used for four-probe measurements, which is just to measure the quantum Hall effect and all these things. So they had to have all these probes and stuff that we didn't even need. But I just wanted to give you guys an idea of the scale and stuff. And this was actually the experimental setup that I worked with. And so we had the bismuth selenide on a substrate in a chip holder in this chamber, and in the chamber, which we pumped down with like a turbojet thing that pumped it down to like vacuum conditions, and we had liquid helium feeding into a capillary that was in direct thermal contact with the chip holder, so that we attained the temperatures of about 4 Kelvin in our experiments. And we used first a normal laser that was like 520 nanometers in wavelength, but then we like upgraded to a super awesome, dangerous class 4 super continuum laser. That was awesome. We upgraded to that, and so just a picture of it. Here's where the actual flakes were. We had a comfortable microscope. We had CCD cameras, and the laser light came into this, was focused back into the optical setup. We had a photo detector that gave us information. Okay, so this is an example of a bismuth selenide flake, and I wanted to show you guys what photocurrent looks like. Basically, the colors mean that there's photocurrent there. The different colors mean that they're different in direction, but that's what photocurrent, and that's what actually fed into our computers. This is what we had: spatially defined photocurrent. This is actual, real, spatial active things. And so what we did, we took this map with this photocurrent map. We graphed it. This is distance versus distance, and the aim of this was to extract the magnitude and direction of the photocurrent in bismuth selenide. And this is the main graph that I want to draw your attention to. You can't really see it here, but this is just space, like X in micrometers. It's just here. And here's the magnitude of the photocurrent and the direction. And so I want to draw your attention to here. As I told you before, we wanted to see whether, yeah.
So this varies with distance then, this graph. So is it that it's clumped up in more places, or
No. This is a line cut of the signal. We focused around the places where we saw photocurrent generation. So the reason why you have, for example, photocurrent here and photocurrent here, but not here, is because here it's clouded by like stuff, like contacts and stuff like that. But this is actually the flake.
Wasn't that the gold?
Yeah, the gold, yeah. And so we focused around the areas. We did like a line cut of this to see how strong the photocurrent was and in what direction. And so that's what we have.
So that's the bottom.
Yeah. So here I want to draw our attention to here. This is what's important. As I said before, we wanted to see what generated photocurrent in bismuth selenide, and we wanted to see if there was a signature of the photothermoelectric effect. And what tends to happen is that in the photothermoelectric effect, the decay of the current should be linear-ish. And as you can see, it is linear-ish in both cases. And this is the decay of the photocurrent in bismuth selenide. This is from the gold in bismuth selenide. And so the linear-ish relationship hints at a photothermoelectric effect. However, this is data that we got from like half of our samples. The other half didn't work. Like I said, so what we try to do is to make sure that the samples were okay. Is we try to do measurements that try to replicate the exact same measurements that they had done a year before when they were brand new. And we didn't get the same numbers. We didn't really get the exact stuff. So I wouldn't trust the other measurements too much. And I would say I'm suspicious of this. I wouldn't say it's like conclusive evidence for the photothermoelectric effect in bismuth selenide. I would say it's preliminary. And
No,
so,
but is there any expectation what the behavior will be, or this is just absolutely pioneering it, something that you...
so we went into this without expectations. We don't want, because you can trick your brain to thinking or into seeing things, right? Especially if you want to see a photothermoelectric effect. But I guess it's not too far of a reach to say that there is photocurrent generation due to photothermoelectric effect, because bismuth selenide at the surface is a graphene lookalike. And since in graphene you see this effect, maybe, it's not too far of a stretch to think that. But we went into it not really expecting it. So that's what we saw, and I want to show you a little bit of the temperature independence of this. We took measurements at 4 Kelvin and at room temperature, and as you can see, we have pretty much the same signal. And so, as I said before, we did trials in other kinds of flakes and other kinds of devices, but that had this bismuth selenide. We did, with the super awesome laser that was infrared light. We did with normal light. We did low temperatures, high temperatures. We did all kinds of measurements, and the conclusions that we came to is that no matter what the conditions of the experiment, photocurrent was generated in bismuth selenide. And that's something that no one had done before. All the measurements, or well, at least that we know, all the measurements that were done in bismuth selenide were just like normal pro measurements of just conductance and resistance and all these things that were dark measurements at low temperatures and stuff like that. And what we did is we brought light into the picture, and so we saw that there was,
The different wavelengths of the light emitted from the laser, did they change lines with them?
Not really. And the reason why, I guess, I didn't want to go too much into it, but the reason why we changed the wavelength of the light in the first place.
Yeah.
No, well, yeah, to check what was the response, but also because in the other flakes that we fabricated, the substrate was silicon, and silicon is supposed to freeze out at below like 77 Kelvin or something like that. When bright freeze out means that it's supposed to become an insulator because it's a semiconductor. But at lower temperatures, it's supposed to freeze out. And when we measured, it didn't freeze out. So what we figured is maybe if we do infrared light is below the band gap of silicon, maybe we'll freeze out silicon. So we did. But it was an excuse to get a new laser, so whatever. And so I would say that the photothermoelectric effect is suspected, but it's a preliminary. I wouldn't say it's a premature conclusion. And so the future work is to fabricate new devices, to not get hand-me-downs, and devices that we can rely on, that are reliable. By reliable, I mean these kinds of standards, like they have definitely an insulated filter, as I said, that was a problem. They're geometrically optimized for our purposes. I mean, they don't have like all these gold contacts and all these things. We just want a clean flake with 2 contacts that we can just do stuff on. And so, of course, more photocurrent measurements and IR and other types of wavelengths. And I'd like to thank the people that helped me out this summer. And that's it.